New anchor tech could shift offshore wind economics. As floating offshore wind scales from concept to core infrastructure, one of its biggest constraints isn't turbine performance, it's anchoring. Traditional anchoring systems, designed for oil and gas rigs, now struggle to meet the cost and volume demands of renewable energy. Mooring can eat up as much as 20% of total project spend in floating wind, a significant jump from the sub 1% cost share it held in fossil fuel applications. And with global capacity projections pushing toward 270 gigawatts by 2050, the sector could need upwards of 40,000 anchors. Enter the deeply embedded ring anchor, DRA, a new system engineered by Texas A&M University alongside teams from the University of Massachusetts Amherst, University of Maine, and UC Davis. Instead of scaling up existing hardware, DARA offers a ground-up rethink, smaller, deeper, and tuned to the deployment realities of renewable energy. Unlike traditional big steel solutions that rely on mass and footprint, DARA maximizes holding power through depth. By embedding the anchor deep into the seabed via a custom follower system, the design achieves greater load capacity while minimizing size and material requirements. That enables fabrication in existing shipyards and avoids the need for heavy lift vessels, two major constraints in the floating wind build-out. DARA's design flexibility also allows for efficient installation in a range of geologies. It can be embedded in soft clay using suction or in layered sands with vibratory tools. This adaptability is particularly relevant in Asia-Pacific regions like South Korea and Taiwan, where geotechnical complexity, seismic risk, and strong currents add layers of challenge to offshore deployments. Beyond turbines, long-term impacts on cost, timelines, and marine infrastructure. DARA's design doesn't just aim to anchor turbines. It's a structural innovation meant to compress project timelines, reduce dependency on specialized port infrastructure, and improve the economic viability of multi-gigawatt wind farms. Its smaller size and deeper placement also make it more resistant to seabed instability issues such as scour, liquefaction, and current-induced movement, reducing maintenance needs and risk exposure over a project's lifecycle. The technology was first advanced in Professor Charles Obenny's lab at Texas A&M in 2017, with doctoral researcher Yunho Lee playing a key role in its development and commercialization. Their work reflects a broader push to align renewable energy hardware with scalable manufacturing and deployment, rather than adapting one-off legacy systems. DARA's utility may also extend beyond offshore wind. Applications could include wave energy platforms, marine charging infrastructure, deep-sea aquaculture, and even subsea data and power networks. In each case, the value proposition remains consistent: cost-efficient anchoring that can be adapted to local conditions without reinventing the surrounding infrastructure. As governments and developers accelerate toward 2030 and 2050 climate targets, technologies like DARA will play a quiet but crucial role. The offshore wind sector's next growth phase will depend as much on what's beneath the waves as on the turbines spinning above.